So next up, we'll have Wenjia talking about merging gradual typing.
Hello everyone. Welcome to my talk. My name is Wenjia. Currently I'm a postdoc in National University of Singapore, and I'm glad to be here. Today I will introduce the joint work merging gradual typing with my PhD supervisor Bruno in the University of Hong Kong and Matías from the University of Chile. In some calculi with intersection type, they use a special operator called a merge operator, and we use double comma, and it allows building values that can have multiple types. For example, in the program, x has both an integer and a Boolean value. And when x is used, it can act as either an integer or a Boolean. And the semantics of the merge operator is type-directed, which it means that components are extracted from merges based on types. So, like in this typing rule, one merge with true is typed as int and bool, and we can always extract a supertype from a merge. And the interaction between subtyping and the merge operator is subtle. So let's see, in this program, x has type L2 and bool, and the value for x include a field L1, which is hidden due to subtyping. Then the merge operator appears to be statically safe. However, what happens when we do the field lookup? If the original field L1 is preserved in x, then when we later look up L1, there will be two L1 fields. And if we use a bias lookup, which return either the first value from the left or the second value from the right in the merge, then the semantics of the program may reduce to a surprising behavior. For instance, in this program, string boom will try to add to an integer, which will crash the program. And note that the type-directed extraction of values can lead to ambiguity. Consider the program. This program is ambiguous because the result can be either 1 or 2. And to address the ambiguity problem, as well as the problem arising from the interaction between merges and subtypings, which I mentioned before, so some restriction is proposed, which we only merges values that have disjoint type. So disjointness will reject ambiguous programs, such as 1 merged with 2, because these two values has the same type int. So they cannot be merged. And merges has many useful things. So they can model complex mechanisms. For example, in calculi with a merge operator, multiple field records are merges of single field records. So they can be extensible at runtime. So they can solve like expression problem. And the merge operator can encode various other programming language features, including extensible records, dynamic typing, and operator overloading. And recent research have further shown programming language design such as Gradual or CP based on variant of merge operator. And this design enables some advanced OOP features such as first-class classes. And in particular, calculate a language with the merge operator can model, as I say, dynamic or object-oriented programming features such as first-class classes and dynamic inheritance, which are supported in TypeScript. For instance, in the above CP language, circle extends shape with a method to calculate the area of a circle. And the superclass shape is a function parameter, which means that circle can be extended by any shape at runtime. But however, CP is a static language, which is restrictful thing. So the question is, what happens if we don't fully know the interface of the superclass? What happens if we would like to extend any trait with this area, and we would like to do something like this, which you can do in TypeScript. But we know that in TypeScript, this behavior is unsound, so we want to be sound. And so we want to make sure to detect the ambiguity error at runtime. For instance, you may extend a trait that already have a class that already have an area function. So to address this, we can follow the gradual typing approach, which combines static checking with dynamic checking, and you can move from fully annotated program to no annotation program. So you can have here, for instance, on the left, a lambda takes a function from int to int and fully annotated. And on the right, you have the same lambda without an annotation. And now with gradual typing, you can have like partial annotated programs. So you have the lambda takes a function from anything to int. So the input can be any type. So what interests is that both gradual typing and merge operator use type-driven semantics. So this is a good opportunity to have a unified foundation for type-directed mechanisms. And we know most gradual languages are built like this. So you have the source language, which have the type checker, and then the separate runtime semantics, which is given by an iteration to a target language. And this target language has its own type checker and runtime semantics. And this is usually called class calculus. So in this paper, we present lambda m star, where the static semantics and the runtime semantics are defined in the same language, where we don't resort to a class calculus or like a target language. And we use a bidirectional type checker for the static semantics and the type-driven runtime semantics. Yeah, so the runtime semantics define over the source language directly. And the interesting thing is that class and projection are mutually defined. So for instance, this is a gradual program which uses merges. And we add this star type, which is unknown, or dynamic type, and it can represent any type. So this is a function that takes merges of records of with type int and with something else. This should be type checked. Then I will introduce some key points and challenges in our work. So one of the key aspects is the disjointness, so which I have introduced before to solve the ambiguity program in merge operator. So for the formal definition of disjointness is that two types are disjoint if they have no common supertype different to top. So for instance, int and bool are disjoint. Int and int are not disjoint. And two functions are not disjoint because they have this common supertype, which is bottom to top. Then how to deal with a star? It's non-trivial. We use the extension lifting of the disjointness. So basically, every type is disjoint with a star because a star can represent any type like top. So the other important thing to mention is that there is a notion of ambiguity error and type error. There is a distinction. So to explain this, we can look at this program. We have merged 1 with 2, and it's cast to int. So you try to cast 1 to int, you get int, and 2 to int, you get an error. But you only want to have one value returned, so you return 1 as the result. Then, if you have 2 values, you have an error because they are ambiguous. Like for example, here with gradual types, you can have multiple numbers, which can be type checked. Even we have disjointness because unknown type is disjoint with any other type, and this could lead to ambiguity error. So this is an error. So you can have this slightly more complex example, like the previous one, but now merge with 3. And if you try to do the same, like the previous one, 1 star and 2 star reduced to an error, and 3 star reduced to 3. So in this case, if we try to apply the first rule, then we return 3. But we don't want to do that, because we want to say that this should be an error, because it's ambiguous. You have 3 numbers. So instead of having an error, we have 2 kinds of error, types and ambiguous error. So we only return a value if the case is a type error. And if one of them is ambiguous error, then we propagate this error. And the other interesting thing is that we preserve modular type-based invariants. So to explain this, we can consider this. B is a subtype of A, and C is a subtype of A. And if you have a program that says let X of type A while new B in E, and you know by modular type invariant that X cannot access full, because X doesn't have full member. This is also true for merges. You can have this program which loses precision on the subtyping lattice, and you are saying X have L1 and type int. And if you bind this X to Y of type star, and then to Z of type L1 and type int, and L2 type bool, then you should not be able to project L2, because X doesn't have a bool. So it should give an error. In this case, our lambda m star reduced to a type error as our expectation. And the last important thing is gradual guarantee. The gradual guarantee is a property in the gradual language which talks about imprecision. So imprecision is a relation between gradual types, where you can say that one type is more precise if it's more static. So for instance, star is the most imprecise type. And the gradual guarantee is separated into the static gradual guarantee, which states that typing is monotone with respect to imprecision. And so if you have a program type check, then a less precise program also type check with a less precise type. And the dynamic gradual guarantee, which says that reduction is monotone with respect to imprecision. So if you have a program that reduces to some values, then the less precise program should also reduce to a less precise value. And the thing is that in lambda m star, the DGG is not satisfied. You can think of this program. You have a variable x that is an int, extract from a merged 1 with 2. Then you have variable y that is a bool, extract from a merged 2 and 4. And z is extracted from both x and y. So first case, 1 is projected. Second case, 4 is projected. And finally, 4 will be projected. But if we lose precision, for instance, now we say x is star, and y is star, and we don't know what to project. And if we try to project bool from x and y, we are going to get an ambiguity error, because we don't know what to project, true or false. So DGG is broken. But we prove the DGG is satisfied, modulo ambiguity error. So here is the original DGG, which says if a more precise 10 E1 reduced to a value, then E2 reduced to a value, and 2 values are in imprecision. And also, if E1 diverges, then E2 diverges. And there are 2 more cases. So we prove the DGG modulo ambiguity error. So in this case, if E1 reduced to a V1 and E2 reduced to V2, and V1 is more precise than V2, or E2 can reduce to an ambiguity error. But here we need to use a semantic notion of precision, because for instance, one merge with true cast to int, you could get 1 if it casts to unknown. Nothing will be projected. And the other case is that if E1 diverges and then E2 diverges or reduced to an ambiguity error. So if you can think of this program here, where the first expression diverges, but the second one gives an ambiguity error because they are 2 integers. So there are more in the paper. You can have a look if you want. So we have the formalization of lambda m star, meta theory, which are proven in Koch. Main theorem are about determinism of reduction, type safety, conservative extension of the static discipline, and the static gradual guarantee. We also have the dynamic gradual guarantee proven on paper. And also we encode the static semantics of GTFL, which is the calculus from abstracting gradual typing. So in summary, our work, lambda m star, which integrate gradual typing and the merge operator, it's a direct gradual language without resulting to a cast calculus. And we support advanced OOP features such as first-class classes and the dynamic inheritance. And we distinguish 2 kinds of error, which are type error and ambiguity error. Moreover, our lambda m star satisfy modular type invariant and dynamic gradual guarantee modular ambiguity error. That's all for my presentation. Thank you for your listening.
Okay, time for questions. I guess we'll start with one. With the merge operator, right? One thing that you said in the original applications that it had was sort of overloading. But here you seem to say that that you rule out cases where basically functions seem to never actually be allowed to have multiple ones merged. So what's the difference between kind of your merge operator and the more classical merge operator?
Actually, our we also consider to allow merges of multiple function, and at first it caused some problem for in the dynamic gradual guarantee, but but we think it should be allowed in the future work. Yeah.
Okay. So how do I think you didn't really show record types, right? Do you have separate record types, or do you just model them as single field records that are merged?
So for record types, we for multiple field record types, we are encoded by a single field records merges. So it's okay. many single field records are merged. So they can be multiple field records.
Okay, but they have individual field names, do they?
Yeah.
Okay.
Yeah, so they have individual field name.
Okay, cool.
What would be a use case for deliberately? So, okay, I guess you showed these 2 types of errors. They're typing errors and ambiguity errors. In the case of a typing error, it doesn't return a value. In the case of an ambiguity error, it propagates that error, right? Sorry, you had a slide. It had 2 kinds of errors, right? There was typing and I think it was this one, yeah. And so it propagates the ambiguity error. Yeah. Yes, that one. And so I'm curious, I guess, about the decision to handle these things differently. From a programmer perspective, when would be a situation where I would want to write code that introduces an ambiguity error, or have this intersection? So why would I, if I were writing code that said something like x is 1, 2, that would give an ambiguity error if it were subsequently used in the code there. Yeah. And so I feel like it would be useful if the compiler would tell me this is ambiguous.
Yeah, if it's dynamic value, like if you annotate it with star, it means that you want to pass the type checker, so it will not detect at compile time, but it will be detected at runtime.
So it's just in the case of star?
Yeah.
Okay, thank you.
Thank you.
Thanks, Ed.